Hello and welcome to my channel DataChaps, where we learn data together. So today in this video, we are going to do a project mine versus rock prediction using logistic regression. So as usual, we'll have some theory first and then do a practical example of how to predict using logistic regression in Python. So let's get started. Have a data set here. This is the sonar data I have downloaded from Kaggle. It has got a good amount of rows, 207 rows, and so many features. And finally, this is our target column. R represents rock, and if there is M, you say this M represents mine. So basically, this data is taken from submarine sensor system. So when submarines are going under the sea, it will sense a lot of objects under the sea. So we just need to identify if that particular object found is a mine or a rock. A mine is a serious threat for the submarine, and how we detect is based on these features. As you can see, there are no headers or column names here. I'm not overly bothered about that one because I really don't need to know the column names personally, because we are trying to find the patterns and understand the data itself. So let's get started with some theory. In this example, we are going to use logistic regression. So that is logistic regression. Don't get confused with the name regression, although this model name itself is logistic regression. In this case, we are using it for classification problem, because I'm not interested in predicting a continuous value like house price. This is a classification value. I only have two classifiers. One is rock and other is mine. So how logistic regression works is it takes all the features and output a particular value that will be between 0 and 1. So that's my 1, that's my 0, somewhere it is 0.5. Let's say if 0 is our mine, anything between 0 and 0.5 will be classified as mine, and anything between 0.5 and y1 is classified as rock. So whatever the value that is given by the output will be converted into 0.1, 0 and 1. That's the nature of the sigmoid function. So sigmoid uses the formula 1 over 1 plus e to the power of negative z, where this e is called Euler's number. It's a constant. Euler's number, it's a constant 2.71828. Like how we have pi is equal to 3.17, this e is the Euler's number 2.5. So whatever the output that is giving us, it will apply this formula. The beauty of this formula is that the sigmoid function is that whatever the number you give in this universe, it will always convert that into a number between 0 and 1. So even if you give 10,000, even if you give 10,000 to this function, the output will be between 0 and 1, maybe 0.1, 0.3, 0.777, whatever it is. Even if you give negative numbers, it will do the same thing. It will always convert into 0 and 1. And the type of classification which we are doing here is called binomial classification. Binomial classification, because we only have two labels, rock and mine. But logistic regression can also be used for multi-class classification. For example, in the iris flower data set we have in sklearn, we have three classifications. One is setosa, virginica, or versicolor, right? Three flower types. We can still use this logistic regression and that particular classification is called multinomial classification. Multinomial classification. When we use a multinomial classification, when we use logistic regression to do a multinomial classification, this sigmoid function will convert into what's called a softmax function, which will derive the probabilities of each set. So discussing about this softmax function can be another video, but in this video we are only concentrating on the logistic regression and binomial classification. Like I said, R means rock, M means mine. We have a set of features here. Now let's get started with our Python code, right? So I have this one here. As usual, let's add a title, which is mine versus rock prediction using logistic regression. This can be a markdown. As usual, let's import the dependencies. So the most important dependencies which we need for this will be numpy. So import numpy as input np, import pandas as pd, and import sklearn dot model selection. It's not import, it's from sklearn dot model selection, import train underscore train test split, and we need to import the logistic regression as well. So from sklearn learn dot linear model import logistic regression. And what else do we need here? We'll need the standard scalar as well. So again, from sklearn dot preprocessing import standard scalar. So what is the scaling and what are the types of scaling available? I've discussed about that in my previous video, so I'm not going to discuss that again here. So we got NumPy, Panda, model selection, linear model, pre-processing, standard scalar. That's it for now. And the next step will be load data into data frame, Pandas data frame. Okay, I'll create that as a markdown. Okay. So in order to load the data into data frame, we have a read CSV function in pandas data frame. As you can see, it accepts a file path delimiter. We don't have any delimiters here, so let's give the file path first. So this will be, in my case, it's datasets slash sonar underscore data dot csv. Let's see how the sonar data is looking, the data frame here. So that's what we got here. We have got 207 rows. From this one, we got 207 rows as well. And one thing I've just observed is, like, you see this one, the top row, which is the header. Because this Excel file did not have a header, it took the first data point as the header itself. So to overcome that problem, what we can say is, within this one, when reading CSV, we can specify if we have headers or we don't have headers. So it accepts a parameter called header, and we can say none. Now look at this one. We got 208 rows. Previously it was 207 because the first data point is taken as a header, and anytime it added some arbitrary header names, some pseudo column names like 0 to 60. These are all our features, and this is our target value. Like I said previously, we don't know the column names, and we don't really have to bother about that one because we are trying to identify the patterns in this one. Now, to train test split, or just to be a markdown. Okay, in train test split, first we have to split our data frame into X and Y, meaning the features and labels. So we can do that by saying X is equal to our sonar data dot drop. We want X to be everything except the last column, because we don't have column names here. I mean it's just a pseudo column name. We can just give that column names itself. So columns is equal to, I want to drop column number 60, and then axis is 1. We don't have to specify the axis, that's the default 1, but we'll do that for. And so now data of 60 is my target value. I'm just going to do that one. Now let's do, drop column axis is equal to 1. What's wrong with this? 60 not found in axis. Okay. Now do x dot shape and y dot shape. So here, as we see, we have 61 columns, right? Okay, 60 columns, which means 61 because the index starts from 0. So that 0, we got this one. So let's look at x. So x has got all the features, and how about y? Right, y has got all the rocks and this one. So while looking at the data, they are all fairly normal distributed. I don't think we need to apply a standard scaling here. It's all decimals except from this one. This is 1, that's okay. Okay, let's see our data distribution. So we can do this by using describe here. Our mean is 0.02 and our standard deviation is 0.02 as well. 0.03, 0.04. Maximum value is 0.13, but 75% of the data is 0.03. It looks like there are some outliers in each of these columns, but let's confirm that using our Seaborn. Import Seaborn as SNS. So what I'm going to do is I'm going to do a box plot of sonar underscore data of 0. Yes, there are outliers. There are quite a few outliers in the first column, and then this one as well. There are outliers. Let's see the data distribution itself. We can look at the data distribution using the hist plot. Using hist plot, sonar underscore data of 0, comma KDE kernel density will actually show the curve. So if I remove this KDE, for example, if I set the KDE to false, we won't see that curve, but when I set KDE is equal to true, we see that curve. So this is something we don't like it, or this is not something that statistics like it. We should not be having a long tail on the right here. These are outliers. We usually want to see a bell curve like this. but a long tail like this means there are outliers. So outliers does not necessarily mean to be treated every single time. Sometimes there are acceptable outliers, because in this, from mean to 3 times standard deviation, we will find 99.7% of our data in this one. That 0.3% is outside this range, but how far outside the range is uh, what determines if there are outliers. So what I'm going to do for now is I'm not going to treat the outliers. We'll just try and fit our model and see what happens. For that one, we have to first split the data into train and test. Have x underscore train, x underscore test, y underscore train, y underscore test is equal to train test split. My x, I know the features. My y, I know test size. Test size, I will give 0.2 as usual. Random state, again, random state is for reproducibility. This can be any number, because when you run this same statement a million times, if you have a random state, you will get the exact same data every time. That is actually useful for reproducing stuff. I'll set the random state to 2, and there is one more thing I want to do, which is called stratify. Stratify is equal to y. So what the stratify parameter does is, if we don't specify this stratify y, we might get a test data which has only rocks or which has only mines. When we say stratify y, we are saying that make the train test split. I want 20% to be test data and 80% of train data. And stratify y means saying that uh, take the 20% as a mix and match of that rocks and mines, instead of just putting rocks in the test or mines in the test. Okay. X underscore train dot shape, x underscore test dot shape, y underscore train dot shape, y underscore test dot shape. Okay, 166 and 42 makes 208. Similarly, 106, 42 makes 208. We have 60 features and one label. Now, time to fit our model. Fit and predict. All right. Now, model. We know our model is going to be a logistic regression with capital L. Logistic regression. We can fit our model on x underscore train and y underscore train. Our model is now fit. It is ready to make predictions. Can do as usual model dot score x underscore train and y underscore train. So I got 80% accuracy on training data. What is it with the test data? X underscore test and y underscore test, it gave me 80% as well. So 80% is not bad at all. Anything between 70 to 90% is treated as good, but we always try to improve that one. So some of this one could be because of the outliers which we have in our data, and it could be because I have not applied any scaling on this one. So what we can do is we can apply a scaling on this and see how that works. Scaling will bring everything to 0 and 1. These are mostly between 0 and 1, but let's see what happens. It's worth checking. It's worth checking. So after this line, before I fit the model, I will use a scalar. Scalar is equal to standard scalar. And as I said before, we should only fit and transform on the training data, not on the test data. So x underscore train is equal to scalar scalar dot fit and transform x train, and x underscore test is equal to scalar dot transform x underscore test. Okay, we have fit that, we have scaled the data. Let's see how this works now. You see, once we scale the data, that the percentage has gone from 80% to 93%. So this is a clear indication that machine learning is understanding the patterns well when you actually bring all the data into a similar scale, right? So there is not a lot of improvement in test data, 83%, but it's okay. And we can treat outliers as well. Treating outliers on the all this 60 columns, checking on outliers. This will make this video very long, which I don't want to do that. Maybe you can take this as your exercise and treat the outliers and see what your prediction score is like. So logistic regression is as simple as this one. That's it I have for now. Maybe in the next video I will try to create a logistic regression with a multinomial classification. Yeah, and one more thing I want to show you here. Class weight intercept calling multi-class is deprecated. So this is the one which used to actually be previously. This logistic regression was only for binomial classification, and we have to specify that multi-class as an extra parameter. But now by default this is multinomial classification. The multi-class problem is side. It is a multinomial random state. Yeah, that's it basically. So multinomial is auto, OVR, or multinomial. So this is how we used to specify previously, but now the default has become auto, so it can do multinomial classification by default. That's all I have for this video. I will do a multinomial classification in my next video. I will see you there. Until then, have a good day. Cheers.